All right, so in this video series, we're going to be looking at Hess's law. And in video 1.1, which we are doing right now, we're just going to do a little introduction on what Hess's law actually is. Okay. Okay, so let's take a look at enthalpy for a second here. So enthalpy is delta H. It's something that we've been looking at in our past couple of lessons and our labs. Now, enthalpy is known as a state function. And basically, what a state function is it's a property that's determined by the state of the system, regardless of how that condition was achieved. So, some examples of state functions are mass, displacement, and temperature. And so, to kind of give you a better understanding of what a state function is, I've put this picture up of two hikers hiking up a mountain as a sort of a little analogy that we can go through. All right. So these two hikers have hiked their own separate paths to get to the top of the mountain. Now we have our blue hiker taking a very direct path up the side of the mountain, whereas our red hiker has gone through a much longer and more winded path to get to the top. Now, if we're looking at this as a state function, um, basically these two hikers have made it to the top of the mountain, right? And regardless of the path they took, if we're looking at this as a state function, all that matters is that these two hikers ended up at the top of the mountain. So it doesn't matter that the two paths were different from each other. Okay, so regardless of how the condition of them being up on the top of the mountain was achieved, what's most important is that they are at the top of the mountain. And so that's basically what a state function is. And we'll see in the next couple of slides how enthalpy as a state function is related to the concept of Hess's law. Okay, so typically what we've been looking at is measuring enthalpy changes of different reactions using calorimetry, right? So, for example, in our calorimetry lab, that's what we did. We measured the enthalpy change of a specific reaction that occurred in water by measuring the heat of the water. And so we use that equation that's on the screen right now. The delta H of a system is equal to plus or minus the heat of its surroundings. However, oftentimes chemical reactions are extremely slow. So, for example, corrosion, if we wanted to measure the enthalpy change of corrosion, it would be really hard to do that because that actual reaction is really slow. It's going to take a really long time for you to actually carry out that experiment. So there needs to be a different way for us to basically get the enthalpy change of certain reactions. And so that's where Hess's law comes in. So Hess's law states that when you have a target reaction that can be broken up into smaller known reactions. So if we'll see here, we have our target reaction that can be added up from the addition of reaction 1, which would be a smaller reaction, another smaller reaction number 2, and another smaller reaction number 3, and we can go on and on. If our target reaction can be added up by a series of reactions like this, then the enthalpy change of our target reaction can be calculated by adding up the enthalpy change of our smaller known reaction number 1 plus the enthalpy change of our smaller known reaction number 2 plus the enthalpy change of our smaller known reaction number 3. And we can go on and on, however many reactions we want. All right, or a more concise way to say it would be the enthalpy change of our target reaction is equal to the sum of the enthalpy changes of our known smaller reactions. All right, so relating enthalpy change back to a state function and using Hess's law to kind of explain that, basically, it doesn't matter what different smaller reactions you add up to get to your target reaction, just as long as you end up getting your target reaction, then we can use that as, then we can use Hess's law to get our enthalpy change for our target reaction, okay? And so sometimes in questions, um, you will be given the different reactions, the different known reactions to add up to our target reaction. And you'll also be given the different known enthalpy changes that match up with those known target reactions. Or, sorry, that match up with those known reactions, those smaller reactions. However, sometimes the question won't give you any known enthalpy changes to match up with your known reactions. And that's typically when you would use this table that you guys see on the screen here. So this is a heat of formation table. And essentially, all of these substances have this specific enthalpy change associated with them for the formation of 1 mole of each of these substances. Okay? And so the specific known reactions that are going to be associated with those values on the table from the previous slide are going to be known as formation reactions. And formation reactions are basically reactions that describe the formation of a specific compound. So if we're looking at H2O, for example, and we wanted to come up with a formation reaction for H2O, it would be made up of its of the different constituents that make up H2O. So the two different constituents would be our hydrogen element, and it would be in its standard state, so hydrogen gas, plus our oxygen element, which would be again in its standard state of oxygen gas, to form 1 mole of our H2O. And you'll see here that we had to balance out the O by adding a half coefficient in front of it, just to make sure that this formation reaction formed 1 mole of H2O. And that's because if we go back to our table here, everything is associated with the formation of 1 mole of the substance. So the enthalpy change that's listed here is associated with 1 mole of the substance, okay? So if we look here at another example, the formation reaction of HCl is going to be made up of its two different elemental constituents. So we have our hydrogen elements in its natural, or in its standard state, which is hydrogen gas, added to our chlorine element in its standard state, which is chlorine gas, and that'll form 1 mole of HCl. And so if we look at our table here, we see HCl gas. So to form 1 mole of HCl gas, it is associated with an enthalpy change of formation of negative 92.307 kilojoules per mole. All right, so this table is going to come in handy for questions that don't give you the associated enthalpy change for your known reactions. Okay, so there are a bunch of steps that you can take to solve Hess's law problems. And so I'll just go over them quickly in this video. You will see them in video 2.1. And if you decide to watch 2.2 and 2.3, you'll see them in those videos as well. But basically, the first step to solving Hess's law problems is to check if the known reactions that you're given add up to your target reaction. And most often, they won't from the first try that you try adding them up, okay? And since they most often won't add up to our target reaction right away, we have to do some manipulations to our known reactions to enable them to eventually add up to our target reaction. And so that's step number 2. And so our known reactions can go through a bunch of different types of manipulations. So we have reversing our known reactions, or we have multiplying and dividing our known reactions by specific numbers to try and match up um, basically the known reactions to add up to our target reaction. Okay, so once you've done all these manipulations, you can try and add all of your known reactions up together again to see if you get your target reaction. And so if your target reaction matches up your known reactions, basically it gives you the green light to add up the enthalpy changes from your known reactions to get your enthalpy change of your target reaction. Okay, so really big important point here that I really want to emphasize is you'll see on the screen any manipulations you make to your known reactions to get them to add up to the target reaction, you have to make those same manipulations for their respective enthalpy changes to get those enthalpy changes to add up to the target reaction's enthalpy change. All right. So you always have to do the manipulations to both the actual reaction and to its associated enthalpy change. All right, and just a peek at the next video. This is the worked example that we'll be looking over if you want to try it out before watching video 2.1.